If I can't picture it, I can't understand it. Albert Einstein. Welcome students. Today in Methods of Work, Energy and Power, we discuss about conservative force and potential energy function. Till so far we have studied work of a force, work energy theorem, its application on a single particle as well as on system of particles in both kind of reference frame, inertial as well as non-inertial. Thereafter, we developed qualitative idea of conservative force, means concept of conservative force. With the help of that qualitative idea, we developed method to calculate potential energy function if force function is given. Thereafter, we developed law of conservation of mechanical energy. And we have applied all these ideas in various physical situations through some examples. Now I can point a fact that at this juncture of time, several students are not as comfortable as they are in force notion to think about this problem. Means they are less comfortable to think about a situation in terms of energy. They say we are not able to visualize the energy. Actually, this is very much required. Today's talk will help you in this way. Now let us think example here. A block here is oscillating to and forth in a spherical ball. Now think if the block were placed here at the bottom, you will see the block will be in equilibrium because there are two forces acting on the block. Its weight acting vertically downward and normal reaction acting vertically upward. So this is equilibrium position and you will see, yes, this is a position of stable equilibrium because if you disturb the block slightly, any side of this equilibrium, the net force, the component of gravity will act toward the equilibrium position and it will make the block to rush toward the equilibrium position if it is disturbed. Now we can think another way that if the block is disturbed slightly on either side of the equilibrium, its height above the ground increases, means its gravitational potential increases. So it seems that block is moving in such a way as to minimize its gravitational potential energy. Now, if you can think in this way, that is what notion of energy. So today's talk will help you to think a problem equally in terms of energy notion also. Now we can describe other types of equilibrium also. Very important thing about stable equilibrium is that it occurs at a point. Now similar to stable equilibrium, there is unstable equilibrium which also occurs at a point. Suppose this ball was inverted and the block were placed at the top, the block will again remain equilibrium. But if it disturbs slightly, it will not return to the point of equilibrium, it will move away forever. So such kind of equilibrium is unstable equilibrium and you have seen it also occur at a point. Now there is third kind of equilibrium, neutral equilibrium. Actually neutral equilibrium always occurs in a region. Suppose instead of ball we have a frictionless horizontal floor. You place the block anywhere, it will be in equilibrium. If you disturb the block from that place to some other place on the same horizontal floor, it will again remain equilibrium. So till what extent the floor is horizontal and frictionless, the block will be in equilibrium. So this is called neutral equilibrium. Now in this all cases, what we can say, in terms of forces you can visualize, in terms of energy you can also visualize. As we have seen in a stable equilibrium, if you disturb the block slightly, its potential will increase and block will try to move towards lower potential state. Now the same thing was in unstable equilibrium. If the block, this ball were inverted, at the top point potential is maximum. Now if you disturb the block will move to lower its potential energy, so it will not return to the point of equilibrium. But in case of neutral equilibrium, potential energy everywhere is same, so the block has no preference to move anywhere. So in this way, we can develop notion of energy to understand any physical process. So before we proceed, let us decide what we do in today's talk. First we develop how to calculate force from potential energy function because we are more comfortable to think in terms of force. So what we do, we derive force from potential energy function and try to analyze situation in terms of force, and then we try to analyze in terms of energy, and whenever required we use a mix-up process or amalgam method. Or sometimes if you are comfortable, we'll think in terms of energy also. So let us proceed first to development of a method how to extract conservative force function if potential energy function is given. Potential energy and associated conservative force. I am saying here associated conservative force because every potential energy is due to some conservative force. For which conservative force a potential energy occurs, that force is called associated conservative force. Now for this, we think about system of particles because potential energy to occur, we need a conservative force, and conservative force is interaction between at least two bodies. So to discuss about conservative force and potential energy, we should start from a system of particles. Now let us see here. In a system of particles, let some of the particles interact with each other through some force fields or material links, and remaining particles do not. So that is general picture of a system of particles. Suppose there are several particles in system. Some of the particles are interacting through some force field or through some material links, interconnecting by string or spring or rods. Some of these forces may be conservative and some of these forces may not be conservative. Remaining particles are not applying forces on each other, so we'll say they are not interacting with each other. Now on the same line, we think about a system, and for system we know that potential energy is function of configuration. How we can define configuration? Let's see. Location of every particle can be defined by its position coordinate with respect to a frame of reference. For each location of a particle under investigation, the potential energy and associated conservative force can be expressed by functions of the position coordinates of the particle. Now, if a system is given, and for every system, what is its configuration? It is set of position coordinates of all of its particle at an instant. And to define configuration, we have to define position coordinates of all of its particle. For this purpose, we have to select a coordinate system that we can call reference frame. And for each location of a particle, suppose for simplicity, what we do, we will not suppose to move all the particle to change configuration. For simplicity, we assume that all particles are at rest, only one particle is moving. So our analysis will be simple. And what we can say, for each location of a particle under investigation, means the particle which you are studying, only that particle we assume to move. So in this way, the analysis will be somewhat simpler. The potential energy, associated and conservative force on the particle can be expressed in terms of position coordinates of that particle. And our purpose is to develop a relation between potential function and conservative force and to extract the conservative force from the potential function. For this, let us assume a particle of finite number, a system of finite number of particles. For example, consider a system of particles P, P1, P2 and P7. We are considering 7 particles. The particles P1, P2 and P7 occupy fixed locations, and particle P is under investigation, means particle P will move. At very location of P, interaction forces from other particles and potential energy associated with each conservative interaction force can be expressed as functions of position coordinates of particle P. Now let us visualize it. Here we are assuming system particles P1, P2, P3, P4, P5, P6, P7. We have seen that some particle will apply force on each other through some force field. So there is no material link in between. And some particle may be interconnected through some material link. That may be a spring, that may be a string, that may be a rod. So if we are assuming P5 and P are connected through a spring, other particles are not connected. Let us see how many forces are acting. Let's, for example, here, these forces. You can see F1. This F1 is interaction force on P because of P1 through some force field. Similar F2. But here F5 is because of a spring, and P3 and P and P4 and P are not interacting. Similarly, P6 and P are not interacting. It means there is no force of interaction between these pairs of particle. And P7 is applying a force on this particle through some force. Now you can see F1, F2 and F7 are attractive forces, and F4 is a repulsive force, field force. So this general picture we are assuming here. Now let the net conservative force on P and the potential energy function be denoted by F vector and U. at an infinitely close location, they are denoted by f plus delta factor and u plus delta u respectively. We can express f and dr. Now what we infinitely close? Suppose at a position vector, force is f and potential is u, and a very close position vector r plus delta r. The force is f plus delta f and potential energy become u plus delta u. Now we can express f and delta r in terms of Cartesian coordinate, because here we are using Cartesian frame of reference. We are starting our discussion with Cartesian frame of reference because we are more familiar with Cartesian coordinate frame. So f will be fx I cap plus fy j cap plus fz k cap, and dr vector will be dx I cap, dy j cap and dz k cap. Let us see here. F vector is fx I cap, fy j cap and fz k cap, and dr vector is dx I cap, dy j cap and dz k cap. Now from this we try to find potential energy and the reverse process, how we can extract force from the potential energy. And to write potential energy, we have used definition. Definition of potential energy suggests that del u is equal to minus f dot dr. That we are very familiar, that negative of work done of conservative force is equal to increment in potential energy. Now in this definition we substitute the expression for f and dr vector. So what we get? Substituting expressions for f vector and dr vector in the above equation, we get du is equal to fx I cap, fy j cap, fz k cap minus here dot. We put the value of dr, dx I cap, dy j cap and dz k cap. Now we perform dot product. So what you get? Del u is equal to fx del x plus fy del y or fz del z, or we can say delta u is equal to fx delta x, f for delta y and fz delta z. Now what we have an idea, that is here a special kind of derivative is used, that is known as partial derivative. What is partial derivative? If a variable or if we have multivariable function, means function of several variable, so we can differentiate that function with respect to any one of the variable or all the variable. Suppose we are differentiating the function with respect to any one of the variable, assuming all other variables constant. So that kind of derivative is called partial derivative. So let us first discuss about partial derivative. The above equation is a multivariable function. Derivative of a multivariable function with respect to any one of its variables holding other variables constants is known as partial derivative. I'm again explaining what is partial derivative. If we have a multivariable function, differentiation of function with respect to any one variable, assuming all other variable constant, is called partial derivative. Similarly here, partial derivative operation with respect to variables x, y and z are denoted respectively by symbols. Actually, as we have given symbol dy by dx to derivative, so similar symbol we give to partial derivative, but in place of d we'll use a curly d, is called del. Say here this del by del x, this operator is partial derivative with respect to x. Similarly, what will be operator for partial derivative with respect to y? Is del by del y, this way. And similarly for z, del by del z. Now after developing or understanding the concept of partial derivative, what is that effect? Suppose we differentiate this equation with respect to partial derivative. Actually this equation is in terms of differential, so there is no need to differential. If we apply this idea here, we want to calculate partial derivative with respect to x only. It means we have to assume y constant, z constant. So dy will be, this delta y will be 0, delta z will be 0. So these two terms will be 0, only this term remaining. We'll divide by delta x and put limit delta x tends to 0, we get this one. So remaining is only minus fx. Similarly, if we partially differentiate this with respect to y, we'll get minus fy, and similarly for z, minus fz. Employing the idea of partial derivatives with respect to variables x, y and z respectively, in equation 1 we get what? Fx is equal to minus del u by del x. Similarly, Fy is equal to minus del u by del y, and Fz is equal to minus del u by del z. So in this way, we have calculated each component of force. Now we can express the force in terms of Cartesian component. What is the expression? Substituting these expressions in F is equal to Fx I cap, Fy j cap and Fz k cap, we get what? F is equal to minus del u by del x I cap minus del u by del y j cap minus del u by del z k cap. That is what the way how we calculate force if potential energy function is given in terms of Cartesian coordinate. But we can have one more notion of notations. Actually, we can write this equation this way. Say F equal to minus I cap del u by del x plus j cap del u by del y plus k cap del u by del z. Here minus sign we have taken common. Now what we gain further? The above equation relates a conservative force with the associated potential energy function in Cartesian coordinate system. What I told you earlier, that this is the way how we calculate the force, either this way or that way. But every time we will not write it, because writing in such an expression, large expression, will be time consuming. So we have to give it some symbol, and that symbol is called a mathematical operation. Let us see what is that. This mathematical operation is called as gradient. Gradient of a scalar function. Why? Because potential energy is scalar function. So this operation is performed on potential energy means scalar function. So it is called gradient of a scalar function. Let us see what is that. The idea will develop with the help of the formula of the force what we have used for potential energy. Say the relation of potential energy with the associated conservative force can be rewritten as, how we can rewrite? Let us see. F vector is equal to minus I cap del by del x plus j cap del by del y plus k cap del by del z u. Here these terms under this bracket are not any physical quantity. They are mathematical operation. What does it mean? That we can say simply that this expression under bracket we are multiplied by u. Actually, we are operating u with this operator. What this means? We have to first partially differentiate u with respect to x, then with respect to y, then with respect to z, and write the sum. So we'll get the formula what we have developed earlier. Once we have separated the operation from u, we can give it another small symbol that is called this way, minus del vector u. So this whole operation is given this symbol. So wherever this symbol will appear, we assume that we have to perform this operation in Cartesian coordinate, or it is called in words grad. So minus grad of u means we have to take gradient of u. We have written grad, it means we have to mean this one, and what does it mean by this symbol? This way. So we have given a symbol to this mathematical operation, del. And now why this term is called del? Actually, this resembles with inverted Greek letter. Here, the term in bracket collectively denotes a mathematical operation. This operation on a scalar function is known as gradient of the scalar function. Actually, the entire idea I have summarized here. What? Here the terms in bracket collectively denote a mathematical operation. I have told you that this is not a physical quantity, it is an operation. So this collective terms are known as an operation, and this operation is known as gradient, and it is of a scalar function, so we'll call it gradient of a scalar function. Now we come how this symbol we have given grade delta u, and we call it del operator or nebula operator. Why you call it del operator and why you call it nebula operator? Actually, this symbol resembles with Greek alphabet delta, inverted delta. That's why the name derived, del. Again, at the same time, there is a musical instrument, harp. That musical instrument in Greek language is called nebula, and that musical instrument resembles an inverted triangle. So from where this word nebula is derived. See here, the operator is known as del operator or nebula operator. This del is equal to, or nebula operator is equal to I cap del by del x plus j cap del by del y plus k cap del by del z, because what we have developed or what convention we have made, by these terms collectively are known as del operator. Now we come, why, from where, or why this name del or nebula are given. The name's del is due to resemblance of the symbol this with inverted Greek alphabet delta. And the name nebula is due to resemblance of the symbol with the Greek name nebula of a musical instrument that we know now as harp. And this is the musical instrument. You can see it wooden triangular frame, that is inverted triangle, and here are taut string which are just strung, just like guitar or some other taut wire instrument. So you can see this symbol resembles with this instrument, and this instrument nowadays called harp, but in Greek language it is called nebula. So this operator is given them nebula operator. Here it is very important to just understand that one, because we know the origin of name nebula. Here general expression of del operator. Actually this expression we have developed in terms of Cartesian coordinate, but sometimes we have to use polar coordinates also. Or when you go in higher classes, we have to use a spherical coordinate system, cylindrical coordinate system, and a general coordinate system also. So what is the general expression for this del operator? That we can write from here. Just follow the pattern. What the pattern is? Unit vector into del upon component of dr vector along the coordinate of this unit vector. I'm again saying del operator is what? See the first term. Unit vector along x into del upon component of dr vector on the x-axis. Similarly here, unit vector on y-axis into del upon component of dr vector along y-axis. Similarly for z, you can say unit vector for z k cap into del upon component of dr vector on the z-axis. So this pattern we repeat here and we write it mathematically. So del operator is summation u cap into del upon del r u. So what does it mean? If you resemble this pattern, u means a unit vector for a particular coordinate. So what is del r u? Component of del r vector or dr vector along that coordinate axis. So that let us define them. What is u cap? U cap is a unit vector associated with a coordinate. And what is del ru? Is a component of dr vector along the coordinate axis. So which coordinate you are concerning? This here will be component of dr vector along that coordinate. Now with this general pattern recognition, we will develop expression for gradient in polar coordinate. Let us see how we can write gradient expression in polar coordinate. Expression for del operator in polar coordinates. So let us first introduce what is polar coordinate. In polar coordinate we have an axis that is better known as reference direction, and a point is located distance from the origin and direction from the origin in this way. So here is the reference direction, that is origin. Suppose here is point P. So point P is at distance r, which makes angle theta with the reference direction. So here we have two coordinates r and theta, and that is polar coordinates. Now we define base unit vector for polar coordinate. One you know, that is one is radial unit vector, one is transverse. Means how base unit vectors are defined for any coordinate system. Merely saying a unit vector is along a coordinate axis, no. A unit vector is defined, base unit vector, in the increasing direction of a particular coordinate. So for r, the radial unit vector will be defined the increasing direction of r, assuming theta is constant. So this will be r cap, radial unit vector. And on the similar fashion, transverse unit vector will be defined in the increasing direction of theta, keeping r as constant. So if you make r constant, increase theta, so this point will move here in this direction perpendicularly. So this will be what? Theta cap, transverse unit vector. Now let's suppose we have introduced you about radial and transverse unit vector. Now our purpose is what? To write component of dr on these unit vectors. For that, let us assume a dr, infinitely small displacement particle, say here dr vector. This particle moves from here to here, so this dr vector. Actually, when particle moves here to here, the position vector will become r plus dr vector in this way, and this angular coordinate changes by angle d theta. Now, as we know that this is the radial direction, so component of dr in this direction will be what? Radial component, and in this direction transverse component. We can visualize this component in this way. So this will be radial component, this will be transverse component means for r cap this will be component, for theta cap this will be component. So this component simply increment in r, how much modulus of r changes. So this we call it dr, scalar form. So in vector form what we write here, dr r cap, because it is in radial direction. Similarly, the length of this line, of course you can see it is a straight line, but in limiting case we can assume it is a arc, and in limiting case when d theta tends to 0, this will be almost straight line as we had drawn here. So this arc length will be equal to radius into angle. So it will be r d theta, and theta cap is in this direction. So this component is what? This r d theta into theta cap. So these are the two components, one along the radial direction and one along the transverse direction. So now we can express dr vector in terms of polar components. So dr vector is dr r cap plus r d theta theta cap. Now we are in a position to write expression for gradient in polar coordinate. For that purpose we write the mathematical general expression. What? Del operator is summation of u cap into del upon del ru. What is u cap? A unit vector for a coordinate. And what is del ru? Component of dr vector along that coordinate. So let us write the mathematical general expression, summation u cap del upon del ru. So in polar coordinate the first term will be r cap into del upon this component del r. So r cap into del upon del r. The second term will be theta cap for u, del upon r del theta, because here this component is r del theta. So let us write the gradient or del operator in polar coordinate. So this r cap del upon del r plus theta cap del upon r del theta. So in this way we can write easily the del operator in terms of polar coordinates also. Why I have given this much time for this? Because sometimes we may be in need to write this operator in polar coordinates also. So what we idea for the study, expression of force from its potential energy function. Actually the expression of force from potential energy function we have written in Cartesian coordinate. Now we extend the same idea to polar coordinate. So first, before we write in polar coordinate, let us rewrite the force, how to write force from potential energy. So in Cartesian coordinate, because we are more familiar in Cartesian coordinate. So, but basic formula is what? F is equal to gradient of u or del u. So we have to put the value of del operator in Cartesian coordinate as well as in polar coordinates. So in Cartesian coordinate, F is equal to minus I cap del by del x plus j cap del by del y plus k cap del by del z and u. It is not into u because it is a mathematical operation. Now how we calculate? So when we operate this operation on u, this will become minus I cap del u by del x plus j cap del u by del y plus k cap del u by del z. This is partial derivative of u with respect to x. Means when you differentiate or you calculate this term, we had to assume all y and x, y and z constant. Similarly here, when you are using this, finding this partial derivative, we have to assume x and z constant. Similarly here, to evaluate this partial derivative, we have to assume x and y to be constant. And how we have written this one? Because del operator in Cartesian form is this way. So I am writing here again. So del operator is what? I cap del by del x plus j cap del by del y plus k cap del by del z. Now in polar coordinates, how we can write? F vector is equal to here r cap del by del r plus theta cap del by r del theta, you can see here. Now when we perform this operation, what it will be? Minus r cap del u by del r plus theta cap del u by r del theta. When we evaluate this term, we have to assume theta to be constant. Now when we are evaluating this term, we have to evaluate r to be constant, but here there is division of r. So here it is not differentiation with respect to r. So in this way, we can calculate force from potential energy function in both kinds of coordinate system, Cartesian as well as polar. Now I will again write here this formula here. What is meaning of del operator in polar coordinate? So r cap del by del r plus theta cap del by r del theta. Now after developing how to calculate force function, if the potential energy function is given, we'll try to use this idea to some example problems. Example 1. The potential energy for a particle moving on the x-axis is defined by the equation U is equal to x4. Its total mechanical energy at x equal to 0 is 2 joule, and the only force acting on the particle is a conservative force. Find the positions where kinetic energy of the particle is 0 and forces on these on the particle at these locations. Actually, intentionally, I have taken here a very simple example involving one-dimensional function. Of course, to know the meaning of this partial derivative and how we calculate force from potential energy, we take few examples involving only one dimension. Later, we develop meaning of gradient in 3 dimension. What is meaning of this gradient operation in 3 dimension? Later on, we'll try to apply this idea on 3-dimensional function also. So what we do, simple idea, since no non-conservative force acts on the particle, its total mechanical energy must be conserved. The locations where kinetic energy is 0, what does it mean? For that purpose, it is given all the forces or the only force acting is conservative, so its mechanical energy will be conserved. So we can use law of conservation of mechanical energy to find locations where kinetic energy is 0, because K initial plus U initial is equal to K final plus U final. Initial K is given and initial U we can find at x equal to 0, 0. And it will equate it with final K, that is 0, and final potential energy this way. So what we write here, Kx plus Ux at any location is equal to E, that is mechanical energy is constant. And this mechanical energy is what you can see here, that is the potential energy at x equal to 0, so it's 0 and 2 joule. So total mechanical energy is 2 joule. So let's substitute the value. 0 plus this potential function is equal to total mechanical energy 2 joule. By solving this equation, we can find very easily that x is equal to either plus 1 or minus 1, or plus 1 and minus 1 both. So at these two locations, kinetic energy of particle is 0. Now we have to find force at these two locations. So first we find expression for force and then substitute these coordinates in the expression of force. The only force on the particle is the conservative force storing the potential energy. This force can be calculated by the famous del operator. So what we do here, F vector is equal to minus I cap del u by del x plus j cap del u by del y plus k cap del u by del z. Now you can see this potential energy depends only on x coordinate. So this derivative and this derivative with respect to y and with respect to z will be 0. So only remaining this term minus I cap del u by del x. So what we have, F vector is equal to minus I cap del u by del x. And now as here only x variable are there, so this partial derivative is similar to usual normal derivative. So now if you differentiate u with respect to x, what you get, 8x raised to the power cube 3. So we can write here force function is minus 8x cube I cap. This is the expression for force, but it is required to find value of force at the location where kinetic is 0. So these locations are x equal to plus 1 and minus 1. Now we substitute these values here and it is very easy. When you substitute x equal to plus 1, you get minus 8 joule I cap. And if you substitute x equal to minus 1, what you get? Plus 8 joule. So substituting the value here, the forces at location x equal to plus 1 and minus 1 are F is equal to minus 8 I cap Newton and plus 8 I cap Newton. So that was very simple example. Now we take one more example involving only one dimensional function. Example 2. A particle of mass m is subjected to a one-dimensional force, potential energy of which varies with x coordinate as u is equal to ax square minus bx cube, where a and b are positive constants. So the potential function is given, and it is given that the particle can move only in one dimension, and that dimension is along x-axis. Now mass of particle is m. What we have to calculate? Find the force as function of x coordinates, and for this we have to use the simple del operator, and again there is only x coordinate, so we can write very simply what F vector is equal to minus del u by del x I cap. So let us proceed. F vector is equal to minus I cap del u by del x plus j cap del u by del y plus k cap del u by del z. But here u does not depends on x, y and z. So these two terms will be 0. So what is remaining here? F vector is equal to minus del u by del x I cap. So this derivative here, if you see it, there is no y and z term. So this partial derivative will be similar to our ordinary derivative. So what it will be? Let us write. F vector is equal to minus 2ax minus 3bx square I cap. You can see here derivative of x square is 2x and x cube is 3x square. So we get this. So that is expression of the force. It means force as function of x coordinate we have found. Now let's come on B part. So that if velocity v naught at the origin is v less than vc, where vc is a certain critical velocity, the particle will be confined in a region near the origin. Also find vc. Actually, let us again understand what is problem. If at the origin particle is given a velocity, that velocity is smaller than some particle value, that is called critical velocity vc, and we need to find vc such that particle will confine near the origin, means particle will move away the origin and return to the origin. So it will keep on oscillating about the origin. It means there must be a point of return. So you can see where are point of return, at where particle returns in one dimension, at that point its speed is 0. That notion we are taking from kinematics. When speed is 0, kinetic energy is 0. Now you can see what the notions we have developed till so far in kinematics and Newton's law. That notions we are mixing with a notion of energy. So let us proceed here. We first explore the local minima and maxima of the potential energy function. Let us explore maxima and minima, and how this maxima and minima will be helpful I will explain you later. So for maxima and minima, derivative of u will be 0 with respect to x, because it is function of x only. So derivative of u means modulus of force is 0. So we have differentiated here, so we equated 0. So del u by del x equal to 0. It means 2ax minus 3bx square equal to 0. So what it gives? X equal to 0 and x is equal to 2a upon 3b. There are two roots, x equal to 0 and x is equal to 2a upon 3b. We know one thing, that maxima and minima always occurs in alternate sequence. So out of these, if this is minima, it will be maxima, or vice versa. If it is maxima, it will be minima. So we have to decide which point is maxima, which point is minima. For this, we have to perform second derivative test. So what is second derivative? d2y by dx square is 2a minus 6bx. This is very well, very simple calculation. Now we evaluate the value of the second derivative at this point and this point, and see if second derivative comes to be negative, so that will be maxima. If second derivative comes to be positive, this will be minima. So let us evaluate this at this point. So d2u by dx square at x equal to 0, and it is very easy, only 2a. So it is positive, means at x equal to 0 potential function is a minima, means potential is minimum. It has a local minima at this point. It means from surrounding value, neighborhood value, potential at the origin is minimum 1. Now let us see what is the value of this at this point and this point. Actually, if this is minima, so the next point must be maximum, but let us verify it. So d2u by dx square at x is equal to 2 by 3, substitute value here, what we get? Minus 2a. So here it is negative. It means it is clear that potential energy at this point will be a maximum. Now what is that? The only force acting is conservative, so particle total mechanical energy will be conserved. So if we give any kinetic energy to the particle at the origin potential is 0. So the given kinetic energy will be the total mechanical energy. So when particle move further, its potential is decreasing at the cost of decrease in kinetic energy. So when kinetic energy will be 0, it will have the maximum potential energy what it can have. But if that maximum potential energy is smaller than this one, the particle will return, otherwise not. Because let us understand again, before maxima or between origin at this point is minima, this point is maxima, so potential function will be like that. So it will have positive slope. If it has positive slope, it means force is negative. So if particle stops anywhere on this positive slope region, it will return to the origin. If it stops here at maxima, it will stay there. But if it crosses this point, it will move away. It will never return to the origin. So what we do? We have to give as much kinetic energy to the particle at the origin so that it cannot cross this point. That is what I have told you, that why we are calculating maxima and minima. I will explain you later. Now you can see, thinking about a physical situation in terms of energy is not very difficult. Only thing is what? You have to make an idea and reconcile our ideas with what we have learned earlier. So what we do here, thus potential energy has a local minima at x equal to 0 and local maxima at x equal to 2a by 3b. Velocity v naught at x equal to 0, not to cross this, what I explained you, use the conservation of energy. So what? K naught plus U naught at the origin is less than or equal to kx plus ux. Means at x, suppose at x particle returns, so here kx will be 0. But this x can be maximum this one, so we'll use this 2ux at this point. And k naught half m naught square, which is given, and u naught is 0 from this. So let us substitute the values. So half mv naught square plus 0 is less than or equal to 0 plus 4a cube upon 27b square. By putting this value here in this function, you can easily calculate potential here. So it will come here. Now by solving this, you can find velocity v naught. So v naught should be less than or equal to 2a by 3b under root 2a by 3m. So this is the maximum value of v naught. So here, this is Vc. So what is Vc? This one. So the critical velocity we found. You can see, of course, at first sight, it appears to be more mathematical, but again, it has its physical interpretation. And you can understand it very well when you become familiar with these mathematical calculation, and you have to reconcile your idea, what you are thinking in terms of energy with terms of forces and kinematics, what we have learned earlier. Now, again, we have taken this problem as one-dimensional function. We again take one more problem for better understanding involving one-dimensional function. Because I have told you that this how we can calculate conservative force from a given potential energy by using gradient operation. And for this, for simplicity, I am taking example from one dimension. And again, as far as 12th syllabus is concerned or ITJ is concerned, this idea is limited to one-dimensional function only. But we'll develop how we can use this in 3 dimensions later. Before that, we try to understand meaning of this operation gradient in 3 dimensions. But before that, let us take next example in 1 dimension. So example 3, in a region of space, a potential energy function is given by this u as function of r is equal to k by 2a cube 3a square minus r square if r is less than or equal to a, and k by r when r is greater than or equal to a. So what it suggests, u is a continuous function of r because there is no discontinuity at r. So this is function, and this is again one-dimensional function. So we first let us see what is asked in this problem. A, derive the expression for the associated force F and determine where it is repulsive or attractive. Now to find force function, we have to use the operation of gradient, or we have to operate this potential function with del operator. So let us see how we'll do it. F is equal to minus del u by del r E r cap plus del u by r del theta E theta cap. Here I have used another symbol for radial unit vector E r cap, and for transverse E theta cap. In place of r cap, I written this E r cap, and in place of theta cap, I written this E theta cap, because sometimes these symbols are also used for radial unit vector and transverse unit vector. So there is no need to confuse here. It is simply r cap, it is simply theta cap. So now let us substitute the values here. So F is that is del u by del r E r cap minus, and why this term has vanished, because if you see this function, it is function of only r, there is no theta. It means u is independent of theta. So this partial derivative will be 0. So we are remaining only with this term. So again, this is one dimensional problem. Of course, this force is three dimensional because this potential function is spread in three dimensional, but its variation in one dimension, what? Along radial distance from the origin. Of course, it varies in space, but mathematically we can say like that. So we operate this one here. So what will be the force? By differentiation, you can easily write k by a cube r cap when r is less than or equal to a, and when r is greater than or equal to a, k by r square r cap. I will not explain how to obtain this function from this by simply differentiating it. So we have obtained expression for the force F. And now we have to see whether this repulsive or attractive. Actually, repulsive or attractive force means a force which is pulling, and this pull does not require any physical contact. So that force is called attractive. And it is pushing, and this push is, does not require any physical contact, it is called attractive. So if the force is everywhere towards the origin, it means it is pulling towards the origin, it is called attractive. If it is always away from the origin, it is called repulsive. So to be towards the origin, here must be minus sign. So there is no minus sign here also. So in both the intervals, it has plus sign. So it is acting away from the origin. So it is repulsive everywhere. So let us write here. The force acts everywhere, readily away from the origin of the coordinate system. That's why it is repulsive. Let's write for both the intervals. So F is this repulsive when r is less than or equal to a, and repulsive again when r is greater than or equal to a. So this force is always repulsive. Now let us see one very important conclusion from here. Actually, this is a very special kind of force. What? It acts radially, and its magnitude depends only from the distance from the origin or a central point. Such kind of forces will be encountered several times in physics. The most common examples are the gravitational force from a spherical object and electrostatic force from a point charge on another point charge. You can see these forces depends on the distance between them, and they will act either towards the other body or away from the other body. In case of gravitation, it is always attractive. In case of electrostatic force, if the both charges are of similar kind, it is repulsive. If both the charges are of different kind, it is attractive. So these are the two examples of such kind of force. There may be some other examples. I am not interested in listing all such examples, but such a category of or such class of force is known as central force. So let us discuss the idea of central force. What the idea is? A central force is a force that acts either radially away from or radially towards the origin, and magnitude of which at a point depends only on the distance of the point from the origin. Such kind of force is called central force. You can see this force fulfills this criteria because it everywhere acts radially away, and its magnitude everywhere depends on r, distance of the point where we are seeking the force from the origin. So this is central force, and there is general definition of central force. Now we can write mathematically how we can represent a central force. So F as a function of r is equal to plus minus F of r. This is r cap. This F of r is a function of r. It tells the magnitude of this force F and r cap. Plus minus sign means plus means repulsive, away from the origin, readily away. Minus means towards the origin. So such kind of forces are called central force. We encounter several central forces in physics. So there is a need to classify mathematically what a central force is. Again, we will see later that all central forces are conservative. Actually, we want to develop method to identify if a function is given, whether the force is conservative or not. So with this idea, we'll develop today in the last. Now we come on the next part. B. With what velocity should a particle of mass m start at r is equal to infinity to approach r is equal to minus infinity? Means say this particle is confined to move on a radial line, say on this line, here is the origin. So infinitely away here, r is equal to plus infinity. What velocity should be given to the particle so it will reach here at r is equal to minus infinity, crossing the origin? Now, actually, this is a very simple idea that in this process, all the forces or only force which is acting is central force, or you can say conservative force, because potential energy function is defined for that. So mechanical energy of the particle will remain conserved, or you can say mechanical energy of the system will remain conserved. So what we can say, at R is equal to infinity, the particle must be given sufficient mechanical energy to overcome the maximum requirement mechanical energy anywhere during the entire journey. So let us understand this idea. Now the idea, what I have told you earlier, just I will write it and explain the same idea as suitable for this situation. If mechanical energy is conserved for a particle to complete a journey, the initial kinetic energy must be greater than the maximum increment in potential energy during the journey. And if initial potential energy is also zero, the initial kinetic energy must be greater than the maximum potential energy during the journey. So these two ideas are same what I have told you earlier. What I told earlier, that to complete a journey, the initial mechanical energy must be equal to or greater than the maximum required mechanical energy during the process or during the journey. Here in this problem, the mechanical energy is conserved. So the same idea I have written in the light of conservation of energy. So in general, suppose at initial location potential energy is not zero. It is given a kinetic energy. So kinetic energy and potential energy at that location will be total mechanical energy. Now as the particle moves, and during the process, during the motion, potential energy increases. So that increase will be supplied at the cost of kinetic energy. So the kinetic energy must be sufficient to maximum increase in potential energy so that particle will complete the journey. Now, if initial potential energy is also zero, so maximum increment in potential energy will be the maximum value of potential energy. So here I am writing this: if initial potential energy is zero, the initial kinetic energy must be greater than the maximum potential energy required during the journey. So this idea will be helpful here, this problem, because if you see the potential function, initially when R is equal to infinity, the potential is zero. So the current energy given at that location must be equal to or greater than the maximum potential energy value during the entire journey. It means from R is equal to plus infinity to R is equal to minus infinity. It means we have to find the maximum value of potential energy in this interval of R. So the potential energy will be maximum where its derivative with respect to R, that is modulus of force, is zero. Why I am writing here straightforwardly maximum? Because if you see the function, it is monotonical function between origin to R. From origin to R it is decreasing, and from again origin to minus infinity is decreasing. So that function, if you see, you can at once say yes, maximum potential energy will be at the origin. But we can see here by mathematical way, we first equate derivative of u with respect to r to 0 means modulus of force to be 0. So modulus of force 0 means k by a cube r and k by r square. This r is greater than a. So here r cap we have omitted because I am writing here modulus of force. So here this cannot be 0 for any value of r except r is equal to infinity. So infinity plus and minus both are included in the end points of journey. So no need to think about here. So again, where the potentials will be, this derivative will be 0 at this point, r is equal to 0. So at r is equal to 0 means at the origin, derivative potential is maximum. So this point will be a maxima for potential energy. So r is equal to 0, potential energy will be maximum. Now at here you can say r equal to 0. Potential energy is defined for the force. Therefore, the force is conservative. So we apply the law of mechanical energy conservation. Again, here I am stressing the fact here because independent of this part that this potential is defined for the force. So the force must be conservative. That is again by definition of conservative force. So to use law of conservation of mechanical energy, we have to equate the mechanical energy at r is equal to infinity and r equal to origin. And for that, we have to write potential Z at both the locations at r is equal to infinity and r equal to 0. So let us write the potential Z function first. UR is k by 2a cube, 3a square minus r square. R is less than or equal to a, and k by r when r is greater than or equal to a. Now we write the law of conservation energy statement. Now using the law of conservation of mechanical energy, we get k infinity plus u infinity is equal to k0 plus u0. Why k infinity? At initial point, u infinity at initial point, k0 at the origin, u0 at the origin. So k infinity is the required kinetic energy. Suppose we assume velocity to be infinity, so it will be half mv infinity square. And u infinity is 0, you can see from here. That is, if you put infinity, you will get u0. And at the origin, the k must be 0, because the entire kinetic energy must be consumed in supplying this potential energy maximum. And at u equal to 0, we will find the potential energy here. So let us substitute first find these two values from this expression. So what we get? U0 is equal to 3k by 2a, because this applicable here. So put r equal to 0, so you get this 3k by 2a, that is u at infinity, and u at origin, and u at infinity from here, that is 0. Now we substitute these values. So instead of it, what we write, half mv infinity square plus 0 is equal to this 0 and 3k by 2a. So from here we can write v infinity. So complete the journey. V infinity is what? From this, very simple to write, 3k by am, and it should be greater than or equal to. If it is equal to, the particle will reach at the origin, but it cannot cross the origin. But if velocity is slightly greater than this, the particle will cross the origin, and thereafter it will reach the r is equal to minus infinity. So to complete this journey, velocity must be in this range, and that is greater than 3k by am square root. Now we can have some better insight by the part C of this problem. What is that? If the velocity of the particle at r is equal to infinity is 2k by am square root towards the origin, describe the motion. Actually, in the B part, what we have seen, to cross the origin, the velocity must be 3k by am square root, but this velocity is less than that, so it cannot cross the origin. What will the particle do? It will move towards the origin, and before reaching the origin, at some point, its kinetic will be 0, and thereafter it will return, because force is always repulsive. So here the whole purpose is what? To find the point from where the particle will return. The potential energy acquired its maximum value 3k by 2a at r is equal to 0. The initial mechanical energy is smaller than the maximum potential energy. Thus, the particle must return before reaching the origin or position r is equal to 0. That we have understood here. Now what we can do further? Now we explore from where the particle returns. For the purpose, we use the law of conservation of mechanical energy. How? With the condition that kinetic energy at the point of return is 0, that we have earlier explained. So how we can write here law of conservation of mechanical energy? K infinity plus u infinity is equal to kr plus ur. Here r is the point from where we are assuming the particle to return. So at this point kr will be 0, and we just calculate ur. This is 0, and k infinity is what? With the help of this speed we will find it. So what? Half m, this 2k by am whole square plus 0 is equal to 0 plus ur. So ur is k by a. Just you can solve it and find it, what you get, k by a. And you can see the k by a value of ur is at r equal to a. So particle will reach at r is equal to a and then return towards the starting point, means r is equal to plus infinity. So what we can say, the particle will return from the point r is equal to a. That is what we explore. Again, if we can draw the potential energy function, the whole idea is very much explanatory. The behavior of the particle is more clearly evident from the graph. So here you can see the function what is given. This is this kind of graph you will obtain. So at r is equal to infinity, u will be 0. So at r equal to infinity, to reach here r is equal to minus infinity as asked in B part, the particle must be capable of crossing this hill. So this must have this maximum kinetic potential energy, and we have seen that is in C part. Now, if kinetic energy given at r equal to infinity is lesser than this potential energy, so particle will reach somewhere here and return. So at r is equal to a, let us see. Now this is maximum kinetic, that is potential energy, and at r is equal to a, this is what. So particle given some velocity, that is kinetic is equal to a, will reach here and at will reach a and return from here. So that is what more clear from this graph. Again, what we can see, we can reconcile idea from the notion of force. What? Up to this region, the potential energy slope, UR slope is negative. So force will be positive, so force is repulsive. So particle is moving against repulsive force, so it will retard and somewhere it will stop and return. It may stop and return or it may cross. So whether it will cross, it will stop, return, will be decided by these energy consideration. Now after developing a proper idea how to use this gradient function in one dimension, our idea is to explore the meaning of gradient function in 3 dimension. What does it mean? As we know, the meaning of derivative is rate of change. So what is meaning of this directional derivative? To understand this, we have to understand 2 more concepts that will be very much helpful in understanding the potential energy behavior in general. And these concepts are concepts of equipotential surfaces and concept of equipotential contours. Let us see what they are. Equipotential surfaces and contours. Now let us see what we can obtain from here. Suppose we have a region in which potential is defined at every point. There is no discontinuity in potential energy function. So at every point of that region, given a potential energy. Now in such a region, it is possible to find set of points at which potential energy are equal. If the region is a plane, so that set of points may lie on a curve, so that curve we will call equipotential contour. If the region is 3-dimensional, and if the set of points lie on a surface, so that surface will be called equipotential surface. So let us document the idea. In a region of conservative force field, where the force is defined at every point, the potential energy is a continuous function of space coordinates. Why? That is, force is derivative potential energy. So if force is defined, derivative potential is defined, so potential energy must be continuous function. So under this reason, what the facility we have? This suggests that we can construct a family of mathematical contours if the force field is 2-dimensional or planar, and a family of mathematical surfaces if the force field is 3-dimensional, such that the value of potential energy remains the same everywhere on such a contour or such a surface. They are known as equipotential contours or equipotential surfaces. Actually, I will recommend you to understand these ideas very well, because they may be very much helpful later on, especially in 12th class when you study about electrostatics. But for a simple idea, let us consider a simple gravitational field of the Earth. So, for example, equipotential surfaces for gravitational field of the Earth are concentric spheres. Gravitational pull of the Earth is normal to an equipotential surface. This idea we can understand because if you have to explore the region far away from the Earth, then the potential energy function what you use we have derived earlier, minus g mm by r. So at same r, what we find, a spherical surface concentric with the Earth center, and with on that sphere, that is mathematical imaginary sphere, everywhere potential energy will be same. So in this way, where equipotential surfaces for Earth gravitational field will be concentric sphere, means concentric with the Earth surface. So we can draw them. This is Earth, and now let us show several equipotential surfaces. Now, what is custom to draw equipotential surfaces? We draw equipotential surfaces with equal interval of potential energy. Now, potential is 1 upon r. So, for each same interval, at higher r, more separation is required. At lower r, less separation is required. So, you can see these two equipotential are having less distance, then more distance, then more distance, then more distance. Now, say anywhere, suppose I want to show the force here, it will be towards the center. So, this is the force. So, you can see this force is perpendicular to this equipotential surface. So, to remember all property of equipotential surfaces, you can remember these examples. Now, we will try to draw some more conclusion based on this discussion, what they are. Since potential energy has the same value everywhere on an equipotential surface or contour, no work has to be done by the conservative force in moving a particle on it, means on equipotential surface or equipotential contour, everywhere potential is same. So if you want to move a particle on this surface, there will not be any work required by the conservative force. That is very, very important property. And what it requires? It requires one more thing, that if conservative force does no work, it means conservative force must be everywhere perpendicular to the equipotential surface or contour. It means it cannot have any component along the equipotential surface or contour. Therefore, there must not be any component of the force parallel to the equipotential contour or surface, and hence the force must be perpendicular or normal to an equipotential contour or surface. That is another very important conclusion. Now, the directional nature of the space derivative in gradient operation indicates this fact. Now it requires little bit deeper concentration. What? If you see the del operator, it requires I cap, j cap, k cap in Cartesian coordinate, r cap, theta cap in polar coordinates. So it is a directional derivative. It means it has vector property or direction property. So we can say, for simplicity, it is a directional derivative. What is that directional property? This directional property must fulfill all these ideas. It means force at any point must be equal to equipotential surface. Now we'll try to learn. This is what this understanding, what we are going to develop now, will help us to understand the meaning of gradient. Now we explore this directional nature of the gradient. That is what meaning of the gradient. For this, we take the same example of force and potential energy. So what the idea is, physical interpretation of gradient operation. What this gradient operation physically means. Before going in abstract mathematical analysis, let us take the example of potential energy function and force, where gradient we are using that same idea. To understand the directional nature of gradient, consider two arbitrarily chosen spatially close equipotential surfaces S1 and S2 of potential energies U and U plus del U as shown in the figure. So here, this S1, I am not using a concentric sphere, an arbitrary shape. S1 potential is defined by U, and very close to it S2. The potential is defined by delta U. So difference in potential between these two equipotential surfaces is delta U. So in moving a particle from any point on this surface to any point on that surface, work has to be done by conservative force is what? Delta U. So that is a very simple idea, and this work will be path independent. Now let us explore further. The work done by the force field in moving a particle from a point on S1 to any point on S2 must be equal. So from here to here, from here to here, anywhere you will move, the work will be equal, because work will be equal to increment in potential energy. So this work is independent of path between these two equipotential, as well as independent of location of the initial and final points. Denoting the force at P by F, this work done dW from P to either Q1 or Q2 is, we denote a point P here and 2 point Q1 and Q2 here, so in this way P Q1 and say Q2, And these Q1, Q2 we have chosen arbitrarily. There is a special property between P and Q that this line path is perpendicular here and perpendicular. In fact, in between this S1, S2 we can assume infinite number of equipotential surface. So what we are assuming here, this path is perpendicular to every equipotential, but this is straight line. So what we can write here, approximately dW is equal to what? Minus du, f dot pq and f dot pq2. Why approximation? Because this here is a curved line. So for that purpose we are using approximate sign. It is not a straight line. So this is what by definition of potential energy. That what is potential energy? Negative of work done by conservative force is equal to increment potential energy, or negative increment of potential energy must be equal to work done by the conservative force. So here this at point P the force is F. So force will not vary appreciably from here to here. So we are using the same value of F here. That's why again here approximation sign, because this is not differential. This is not infinitely close. But we think in terms of infinitely close quantity. If del U will become du, then P and Q1 will be next to next. It means there will be no third point in between them. So this PQ1 can be assumed a straight line. So let us extend our idea in terms of that infinitely small interval. The path PQ1 of length delta r is selected perpendicular to every equipotential surface between S1 and S2 and may have curved shape. The path PQ2 is an arbitrarily chosen straight line of length delta r. That idea I have explained you earlier, that this line is perpendicular to every equipotential surface which can exist here in between, but this is arbitrarily chosen straight line. Length of this is delta r and length of this we can say delta r, not dr. Now F is approximately equal to minus del u upon del L cos theta. Why this on this line? You can see this way. If you use this one, you can write this. And here is what directional property. Because F is not del U upon del L. It will be what? Del U upon del R. So why this del U upon del R? Because this dot product, what does it mean? The product of component of force along del R. That's why here we are taking the component displacement along F. So this is what by definition of work done. Or minus del U upon del R, this way, this is del R. So in the limiting case, when del U tends to 0, PQ1 is tending to 0 means dr, and path PQ1 will become a straight line segment of length dr. So in this case, what we can write here, F is equal to minus du by dr, or dl cos theta, or minus du by dr. So this is what. Now what we can understand from here. Actually, I will suggest you to go through at least twice or thrice with this mathematical analysis. But what conclusion can we draw from this mathematics? Let us see. Now we make final conclusions. For the conclusion, I have drawn this diagram again, and the final result F is approximately equal to du upon dl cos theta, or equal to minus du by dr. And this is S1 equipotential, and this is S2 U plus delta U, and the same situation. What conclusion can we draw? Let us see. This discussion suggests the following 3 points. What the 3 points are? Let us see. First, the path length dr is the least one. Thus, modulus of the derivative is maximum on the path PQ1. Between, if you see, move from point P to any point on S2, this length is the least path. So this value will be maximum. That is what. And what is second point? The force at a point is perpendicular to the equipotential surface through that point. We have seen it earlier. And what is third point? The minus sign indicates that the force is in the direction of decreasing potential energy. It means force must be here perpendicular to this one because of this minus sign. So now these 3 points are for force potential energy relation, and from these 3 points we try to extract meaning of gradient But before that, let us see the force associated with a potential energy function is equal to the maximum space rate of change in potential energy and has direction towards the decreasing potential energy. Actually, if you see the gradient operation in general, there is no need of minus sign. This minus sign is here only for a special case, force potential relation, and for this minus sign, that is what direction of force is toward decreasing potential energy. But if you remove this, only what is remaining here? What this maximum space rate of change. So that is what directional property. Let us cite it. Gradient physical interpretation. Operation of gradient of a scalar function does not include the minus sign. Therefore, only the first two of these points suggest us all about this operation. So here minus sign is says that the force must be toward decreasing potential, but gradient operation does not require in general minus sign. So only the first two conclusion we assimilate to extract the physical meaning of gradient operation. What is that? Gradient of a scalar function is the space rate of change in the scalar function at a point in such a direction as to have maximum modulus. That is what meaning of gradient. Actually, what is meaning of directional property of space derivative in gradient? Actually, gradient is space derivative not in any direction. It is in a particular direction in which the modulus of the derivative will acquire maximum value. That is what meaning of gradient. Now, after understanding the meaning of gradient, let us apply these things to some problems. Find the magnitude and the direction of the associated conservative force for the parallel equipotential surfaces shown in the figure. Actually, we know here this kind of structure. So this is yx, actually z is here. So these are equipotential surfaces. You can see equipotential surfaces, that is it is 10 joule, 20 joule, 30 joule, 40 joule, and they are equally spaced, so it will be 0 joule. Now these equipotentials are parallel, and if you see the force to be perpendicular everywhere and towards decreasing potential, so if you see force will be in this direction, so everywhere force will be what? In same direction. So what we can extract here, the force is unidirectional and direction of force will be what here? Perpendicular to this. So this 90 and this angle 30, so direction of force will be 120 from the positive x direction. The only thing is what? To find magnitude of force. Now you can see here, if you see this line, so along this, this is the direction of say, you can see this, that, several directions you can take. But only in this perpendicular direction, the derivative or gradient have maximum value. So we have to choose this direction only. And let us see how we calculate. Physical interpretation of gradient and force potential energy relation. F is equal to minus gradient of u suggests. Again, we draw the three conclusions. Equispaced parallel equipotential surfaces must represent a uniform force field. Means equipotentials are equispaced. So everywhere their derivative must be same if you take in a particular direction. So such kind of parallel equipotential surfaces represent a uniform force field. Second, the force at a point is perpendicular to the equipotential surface through that point. And third, the force is in the direction of decreasing potential energy. Now with the help of these three ideas, let us choose a point here, say this one. The force is uniform everywhere in the region shown. Therefore, we can calculate it at any point. So if the force is uniform, we can choose any point to calculate. So we choose this point. Consider a point B on the 20 joule equipotential. Say here, this point B, and we know that force is perpendicular and towards decreasing potential. So we have used directional property. Now we have to find only rate of change, space rate of change. So we find change in potentials between A and B and length of this path. So that will be what? This is 10 centimeter and 30. So 10 sine 30, it will 5 centimeter. And difference is what? 10 minus 20 minus 10, 10 joule. So 10 joule by 5 centimeter. So let us do here. We are concerned only in magnitude. So the direction we have decided. So F is equal to UB minus UA upon AB. So this direction we have decided. So no need to put a minus sign here. So UB is 20 joule minus 10 joule upon 10 centimeter sine 30. So it will be 200 newtons. So force everywhere is 200 Newton and direction is what? Everywhere this direction is the same. So that angle is what? I'm again saying here, this angle is 30 and this is 90. So total angle from positive x direction is 120 degree. Direction of the force is 120 degree from the positive x direction everywhere. So that is what? Simple problem we have solved if we know the physical interpretation of gradient. Merely by knowing the formula of gradient will not help you in this case. So actually to be familiar, we must know the mathematical relations as well as the physical interpretation also. Potential energy and nature of equilibrium. That is again very important point that we had discussed in the beginning. With the help of potential energy, we can describe equilibrium as well as nature of equilibrium. If you see the ball and the block example, if the ball was as was shown in the screen, concave up, the bottom point is the stable equilibrium and where potential is the minimum. If the ball was placed inverted, the top point is the location of unstable equilibrium where potential is maximum. And if instead of ball we use a horizontal frictionless surface, so everywhere on the frictionless surface equilibrium is neutral. So what we can see at the when potential is a maxima, there is a location of unstable equilibrium. When potential is a minima, it is location of stable equilibrium. If potential is constant or uniform in a region, that region is for neutral equilibrium. But let us see here. Consider a one-dimensional potential energy function and the associated conservative force. See here, I am choosing a curve which have all kinds of variation, maxima, minima and constant. Now we know that the force is negative of derivative of this. So before we try to draw the force graph, let us see one thing. At this location it is minima, at this location it is maxima, and beyond this location it is constant. So we denote this point as R1 for minima, R2 for maxima and R3 for beyond that constant. Again we know that here this is minima, so it is stable equilibrium, maxima unstable equilibrium, and beyond that neutral equilibrium. But that is what we have to reconcile this understanding from our understanding of force. So let us draw the force diagram here. So the force graph, what we use this relation, force is equal to the negative of the slope of the potential energy curve, because here one dimensional, so gradient will be del u by del r, so slope of this. So if you can draw the negative of this slope, so from here to here slope is negative, so the force will be positive, and here slope is 0, so at this point force will be 0, so equilibrium. From here to here force is positive, so its negative will be force is negative of slope, so from this point that point force will be negative, so and so on. Now we can draw with the help of this graph between F and R. So we have written this statement in mathematical form. Let us see how the graph will be in this way. And you can just qualitatively see the graph will be in this way. See, here the force is 0, here the force is 0, and beyond that force is 0 because derivative potential will be 0. Now you can see at this point, if you disturb the particle from here at this, force will become negative, so it will the particle on that side. So for this stable, again if you shift the particle here, the force is positive, so it will push the particle on that. So this point is stable equilibrium. So we can say again as well that the minima of a potential is location of stable equilibrium. Now let's come on the unstable equilibrium. So here If you disturb the particle at this side, force will become negative, so it will pull the particle in this direction, means away from this point. Unstable equilibrium. Similarly for disturbance on that side. If you disturb the particle slightly here, force become positive, so it will push the particle away from the point of equilibrium. So this point is unstable equilibrium. Here potential is maxima. So maximum potentiality denote unstable equilibrium. And here everywhere force is zero, so this region is for what? Neutral equilibrium. So for equilibrium, what we know? Force is zero. Force is derivative negative of potential energy. So when equilibrium is there, derivative of potential energy must be zero. So when derivative function is zero, it is either maxima, minima or constant. In that way, maxima, minima or constant, we define whether the equilibrium is neutral or stable or unstable. So let us revise all these ideas. From this graph, we can conclude what? The state of stable and unstable equilibrium is associated with a location where potential energy function assumes a minimum and maximum values respectively, and the neutral equilibrium is associated with region of space where potential energy function assume a constant value. So we have written all the ideas. So what we can say: stable equilibrium, minimum u; unstable equilibrium, maximum u; neutral equilibrium, what? U uniform. I'm using uniform because in physics there is a notion that a variable which is not changing with space coordinate is called uniform, and if a variable is not changing with time, it is called constant. But in mathematics, this notion is not followed, and this is special notion in physics. So uniform is anything which does not vary with space coordinates. So in this way, we can decide whether an equilibrium point will be stable, unstable or neutral. Now we use these ideas in a very simple example. What that? Force between the atoms of a diatomic molecule has its origin in the interaction between the electrons and nuclei present in each atom. This force is conservative, and the associated potential energy U as function of R to a good approximation is given by a function known as Lennard-Jones potential. So this information is given. You are not required to raise question on this information. So what potential function is given? U as function of R is equal to U naught A by R raised to power 12 minus A by R raised to power 6. So that potential function is given. And what is asked? And here R is distance between the two nuclei, and U naught and A are positive constants. Develop expression for the associated conservative force. Find the equilibrium separation between the atoms. Let us see here. So to develop expression for force, we take gradient of that. Again, it is one-dimensional function. So we differentiate U with this 2R and put a minus sign. So the force F is minus del U by del R, R cap plus del U by R del theta, theta cap. So it does not depend on theta. So this term will be 0. So we have only this one. So F is equal to minus del U by del R, R cap. And by differentiating it, we can write F is equal to 6 U naught by A, 2A by R raised to power 13 minus A by R raised to power 7. So you can verify the derivative of that. So this is what the conservative force function. Now what we to explore? What is the equilibrium separation? In equilibrium position separation, potential energy must be extremum. It means force must be 0, or derivative potential is 0. So we equate it to 0 and find the separation R, which is the equilibrium separation between the nuclei or atoms. At equilibrium, force must be 0. Therefore, the equilibrium separation R naught is, equating it to 0 and solving it, what you find? R naught is equal to 2 raised to power 1 by 6 A. So that is equilibrium separation between the atoms. So in this way, we have used again the concept of equilibrium. Now we extend our idea or study towards definition of conservative force. I told you in the beginning, that till so far we have understood the conservative force qualitatively, that a conservative force is involved in only energy conversion from mechanical to mechanical, that can be only from potential to kinetic or kinetic potential. It cannot convert mechanical energy into some other forms or vice versa, or some other forms to mechanical energy. So that idea will helpful in absolute manner in all physical situation, but definition is a mathematical description of conservative force that can also be required in some situation when you know the force as a function. If you don't know the behavior of force, only function is given, so how can you identify it is conservative or not? So let us see, this is what the area of this article today. Till so far we have learned that a conservative force stores the work done against itself as increase in potential energy in the force creating mechanism, or the work done by a conservative force is supplied by an equal decrease in potential energy stored. So that was idea. That is, we can write it mathematically, dW by internal conservative force is equal to minus du. That is very familiar definition for you of the potential energy. Energy conversion by a conservative force is either potential to kinetic or kinetic to potential only. Means what we have just I have written from this to that is what we have understood earlier. So we have taken a brief revision of qualitative idea about conservative force. From that qualitative idea, we try to extract mathematical definition of conservative force. The potential energy depends on configuration of the system and not on the path followed by its particle to acquire the configuration. This idea suggests us a formal definition of conservative force. Actually, that is very important idea. If you see the potential as a function, it depends only on the space coordinates. It will not depend how the system has been brought into that configuration, on what path the particle has moved to reach in that configuration. Potential energy depends only initial and final configuration. So we'll use this idea to define conservative force, because potential is defined only for conservative force. So let us see again. A force, finite non-zero work of which in moving a particle from a position to another is independent of the path followed, is defined as conservative force. So here please take care, finite non-zero work. If in moving a particle from one point to another point, we have to do finite non-zero work. If that work is path independent, we'll say the force is conservative. And what meaning this idea can have, let us see. Consider a particle moving from position 1 to position 2 on the paths A, B and C under the action of a conservative force F. So let us see the situation. Here position 1, position 2. This is path A, this is path B. You can see from arrow the direction, and this is path C from position 2 to position 1. So what we can see, if the work done is path independent, what we can write? Definition of conservative force suggests that W1 to 2 on path A is equal to W1 to 2 on path B is equal to W1 to 2 on path C. Of course, it will be negative of W2 to 1 on the according direction. So this we can see. This will be equal to what? Minus W1 to 2 on C. Similarly, what we can write here? That is, it will be equal to minus W1 to 2 on B. This will be equal to minus 1 to 2 on A. But here, we have written here for this direction, 1 to 2, this work. Now what we can write from here? W1 to 2A minus this is equal to this minus that. So this important equation we can write. And this will be 0 because these two terms are 0. This and say this one. Now this first statement we have written from this definition, that work done between two positions must be path independent. If we take 1 to 2, work on that path, work on that path, and work on that path must be same. And from this simple algebraic manipulation, now this will be equal to what? minus 2 to 1. This will equal what? 1 to 2. So what we can write here? W1 to 2A plus W2 to 1B is equal to W1 to 2A plus W2 to 1C equal to 0. What is that? This is moving from here and again here, this 2 to 1 on B. So this is what? A closed path. We have started from position 1, reached position 2, again we have reached position 1. So that kind of path is called closed path. So work done on this closed path is 0. Similarly from here, we are reaching W1 to 2 on path A from here to here. Again W2 to 1 on C here to here. This is 0. So on these two closed paths work done is 0. And these paths are chosen arbitrarily. So what we can say? Another meaning of this statement, that work done on a closed path by a conservative force must be 0. And this we can write mathematically in this way. Work done by a conservative force on a closed path is 0. And this we can write in terms of integral formula, say f dot dr integral, and with a circle sign here equal to 0. This circle sign denotes this integral is on a closed path. So these two definitions at first sight appears to be different, but they are the same things, or you can say two different ways to explain a simple aspect, and that aspect is this one, definition of potential energy. So now here we have defined conservative force. I am again saying here, a conservative force, work done by that must be path independent if the work done is non-zero, or on a closed path work done should be 0. This idea will use to identify conservative force, but other than this there are several intuitive ideas which we can make to identify a conservative force. So what the ideas are, I'll summarize here. How to identify conservative and non-conservative forces with the help of this definition, and what we have studied till so far, we'll try to use all these ideas to easy identification of conservative and non-conservative forces. For a conservative force, potential energy function must be defined. This is a necessary and sufficient condition for a force to be conservative. Means if for a force potential is defined, it must be conservative. But we'll write here again properties of conservative force on which we define or we identify a conservative force. Various outcomes of this condition are listed here for simplicity, because this statement to reach various outcomes is cumbersome. So I am writing here all the outcomes. 1. A conservative force must be independent of time in a concerned time interval. Actually, a conservative force must not depend on time. What does it says? Suppose we are assuming gravity to be conservative. We know that gravity is conservative, but we are moving a point from a particle from one point to other point and again bringing it to the initial point. So that is closed path and the work is 0. Suppose we are bringing the particle from initial position to final position, and we calculate work. But when we are bringing the particle from final to initial position, force has been changed if the gravity were time independent. So now we get different work. So total work done will not be 0. So what is this? Simple argument that a conservative force must be independent of time in the concerned interval. Second, either the magnitude or the direction or both of a conservative force must not depend on velocity. Means for a conservative force, its magnitude or direction or both cannot depend on velocity, or you can say the conservative force must not depend on any way on velocity. Simple example we can take of kinetic friction. Suppose we move a block from one point to other point, say in positive direction, and bring it back to the initial point. We know that the total work done is not 0 because friction is always opposite to velocity. So what we can say? Friction force is opposite to velocity. Here direction of friction depends on velocity. So that is very simple example. So what is second point? A conservative force must be independent of velocity, either in magnitude or in its direction or both. What is third point? A uniform and time independent force is a conservative force. A uniform and time independent force is a conservative force, because for a force to be conservative, it must be time independent. We know the gravity near the earth surface for small moments above the earth surface smaller than the earth radius, gravity can be assumed uniform. But if gravity changes from time to time, then work done on a closed path will not be zero, because in bringing a particle from initial to final position, say gravity has some other value, and again bringing from final to initial, gravity has changed, though gravity is uniform, so work done will not be zero. So for gravity to be conservative, it must be uniform near the surface and time independent. So all forces which are uniform and time independent are conservative forces. What is fourth idea? A central and time independent force is a conservative force, that is gravity far away from the earth, electrostatic force. All these forces, if they don't depend on time, they are conservative. What is next idea? If force is conservative, its curl must be null vector everywhere. What is curl? Curl is again del operation on a vector field with the cross product. So what is this? Del cross f is a null vector. If this is the condition for a conservative force, this condition must be fulfilled. Actually, use of this condition is not advised in 12th class and in JEE preparation. But I have seen use of this condition in several problems in home assignments or in some tests. So I'm writing here this condition. What does it mean? Simply cross product. So del operator is what? Let us see here. That is in Cartesian coordinate system. What we can write here? That is I cap del by del x plus j cap del by del y plus k cap del by del x, and cross product fx I cap plus fy j cap plus fz k cap. Now this cross product we can write in terms of a determinant. What? I cap, j cap, k cap. This del by del x, del by del y, del by del z, and here fx, fy, and fz. So to remember the curl operation here, cross product, this determinant notation is very simple. Now we can open the determinant. What it will be? I cap del f z by del y minus del fy by del z minus j cap del fz by del x minus del fx by del z plus k cap del fy by del x minus del fx by del y is a null vector. And to be this null vector, each term in the bracket must be 0. So this term must be equal to this term must be equal to this term must be equal to this term. So this test is sometimes used to identify if mathematical function is given, whether the force is conservative or not. But what I'll again say, that this test is beyond the scope of IIT or even Physics Olympiad. So I will recommend you, don't be fuzzy about that, but whenever such problem is asked, you must be capable of doing this without any physical insight of this operation, curl operation. Actually, we have to use gradient, so I have explained you the physical interpretation of gradient. But as far as the syllabus is concerned, this operation is not in syllabus, so I will not concerned about developing physical insight of that. This simple mathematical procedure you can do. Of course, in some situation, a force function, if you are able to express it as a central force, then it will be conservative. What I suggest you, try to use these ideas before you use this one to decide whether a force is conservative or that or not. Or you can say path independent idea. How we can use those ideas to identify a force, whether it is conservative or not, let us see in some examples. So example 6, show that a uniform and time independent force is a conservative force. So this is what a postulate idea. So let us see why a uniform and time independent force is conservative. Let us see. Consider a force F is equal to F naught E cap. If it is uniform and time independent, the magnitude F naught as well as the unit vector E cap must be constant and uniform. What is constant? Means time independent. Uniform, they must be same everywhere. Now we calculate work done by this force. Suppose a particle moves under the action of this force from a point A to point B of position vector RA to RB and on an arbitrary path, say on this figure. So this is origin. So this point A has position vector RA, this point B has position vector RB, and I have chosen this arbitrary path. You can choose another path also. Now we calculate work done by this force. So to calculate work done, we have to show the force and an infinitely small displacement at some intermediate stage. What we have done, the same method while calculating work of a force. So here at intermediate state here, this is dr vector and this is what f vector. Now what is dw? F dot dr. At an intermediate position, r vector, an infinitely small path length dr vector, and the force f vector are shown here in the figure. So the work done by the force in moving the particle from A to B is WA to B is integral from RA to RB f vector dot dr. Now we know the f vector is constant and uniform, so we can take it outside. So it will be this. So this is simply f dot product RB minus RA. Now this is what net displacement from A to B. It will not depend on path. It will be this vector always, whether we move on this path or we'll move on this path. So you can see this work done is path independent. So we can say a uniform and time independent force is a conservative force. Now we concentrate our idea on some other example. Before that, what we can see here, work done by a force is equal to dot product of force and the net displacement. That does not depends on the path. That's why it is conservative. So we have explained it. For the uniform force, the work done is path independent and depends only on the initial and final position. Hence, a uniform force is conservative. You can see one thing. Here I have written intentionally uniform. I have omitted the word time independent. Actually, if you say uniform, it is, or you can say if it is not mentioned that a force is time dependent, we have to assume it as a time independent. Actually, it is what? A custom. Suppose I'll say find velocity. What do you find? Instantaneous velocity. We never say average velocity or instantaneous. So instantaneous word is dropped. It is a custom or convention. Similarly here, a convention is followed in physics. If about a force or field, it is not specified, it is time dependent, we have to assume it time independent. So if you say uniform force, means it is time dependent, sorry, time independent. And so we have seen this example. Let us take another example of the same category, how to identify a force is conservative or not. Decide whether the following forces are conservative or not. What the forces are? Part A, F is equal to AX I cap plus BY J cap, and B, AY I cap plus BX J cap. We take these two simple category, and now let us say part A. What we do? Method 1. What is method 1? Path integral or work calculation will show that work done must be path independent. So let us calculate here. So what we do? WA to B is integral RA to RB F dot dr. We put the value of F, and dr is what? Dx I cap plus dy j cap. So RA to RB integral AX I cap plus BY j cap dot DX I cap plus DY j cap. Let us perform dot product operation. So what we will? A, X dx from X to XP, and B, YA to YB, Y dy. Why we have done this one? So this dot product what? AX dx and what? BY dy. So then we use some rule of integration. So while calculating AX dx, we take A outside and we correspondingly change the limit. For RA we take XA, for RB we take XB. Same thing we have done here. Now if you see this one, X dx we can integrate without knowing what the path is. It will be always x square by 2. Similarly here, y square by 2. So this in different integral we can calculate what? XB square minus XA square by 2, and this again YB square minus YA square by 2. So that is work done. This work done we have calculated without knowing the path. So if we can calculate work done without knowing the path, it means work done is path independent. So this force must be conservative. The above path integral depends only on the initial and final positions and not on the path. Thus, the force is conservative. Now that is a simple idea. This idea we can you can use in any problem. Now let us see the next idea. What? Method 2. Curl operation. What I have seen about curl, let us do it. How we'll do it? Force conservative. For conservative force, curl of the force must be a null vector. So I cap, j cap, k cap, del by del x, del by del y, del by del z, fx, fy, fz is equal to a null vector. Now we substitute the values. What? I cap, j cap, k cap, del by del x, del by del y, del by del z. Here ax, by and 0. Now this will be 0. You can verify. Open the determinant. So curl is 0. So this force is conservative. So we have taken this method, and that is what advised to do at 12th class. And if you want, you can do this one. Now we use the same two methods on this part B. Let us see. Here that is you can see, verify it. That is 0. How we can verify? That is this del by del x, say partial derivative. So it we have to assume y constant. So this derivative will be 0. In this way we can so see for all the terms. Thus the force is conservative. For part B, we'll use the same two methods. Method 1, path integral or work calculation. So WA to B is the integral from RA to RB. What f dot dr. So we put the values from RA to RB integral. F is what? AY I cap plus BX j cap dot DX I cap plus DY j cap. Now let us perform the dot product operation and separate by some rule. So it will be A xa to xb y dx and B ya to yb x dy. Now we can see that to find this integral, we know how y depends on x or y as function of x. Similarly here we know how x depends on y or x function of y. So this integration we cannot perform now without knowing the path, how y depends on x and how x depends on y. So now we cannot calculate here. So this force must be a non-conservative force. The above definite integral depends on functions of that y, that x f of y and y of x, thus on the path. What? These integrals depends on these functions, so they must depend on path. So work done is path dependent, so this force is not conservative. The force is non-conservative. That is method 1. Now as method 2, again we take the curl operation. So what is that? For conservative force, the curl I cap, j cap, k cap, del by del x, del by del y and del by del z, fx, fy, fz is a null vector. So now put the values I cap, j cap, del by del x, del by del y and del by del z. What we have here? Ay, bx, this. Now we open the determinant. So what will have? I cap, 0 minus a, minus j, 0 minus 0, plus k, b minus a. Now you can verify this by just using partial derivative, and that is not a null vector. So this force is a non-conservative force. Now today's lecture, this much idea I have to communicate. So what I advise you, to revise all the examples and all the ideas properly. Of course, I have taken problems which are very simple, but again very conceptual. Try to practice these problems at least twice or thrice so that you can understand all these ideas. And later in homework, we'll take more elaborate problems. So thanks for patient listening. We'll meet in the next class. The words of a language, as they are written or spoken, do not seem to play any role in my mechanism of thought. The physical entities which seem to serve as elements in thought are certain signs, and more or less clear images. Albert Einstein.